Hello, my name is Yessine Khanfir. I work as AI research engineer in NLP and Bio AI, and the purpose of this presentation is to present an overview of our work accomplished at InstaDeep in collaboration with the Digital Research Center of Sfax in Tunisia. The outline of the presentation will be as follows. We will begin by stating the problematic within which this work is inscribed and the task that we are trying to solve through our proposed approach. Next, we will discuss a highly relevant previous work, as that was our starting point and our work is based on it. After that, we will tackle our proposed model and its different modules to explain our contributions. In the following part, we will be presenting the evaluation results and the comparison of our model to the state-of-the-art. In the last part, we will conclude the presentation by restating our contribution and the work that led to achieving new state-of-the-art. So the task of interest. The task that we will be performing in this work is the joint recognition of handwritten text and the recognition of named entities in a single-stage manner. The idea is that the model should be able to label words into categories while it's transcribing the handwritten text from the input documents. Our model will be validated and trained on two common datasets in the field of information extraction from handwritten documents. The first one is the Esposalles dataset, which is a collection of historical marriage records written in the 17th century. It comprises 125 pages, 1,747 paragraphs, which is 5,447 lines. So this dataset is imposed as the benchmarking and comparison in the information extraction from historic handwritten records challenge of the robust reading competition. There are two versions of this dataset, the complete and basic one, the latter being the easier one as it only contains 4 annotations or named entities, as shown in this table. Then we have the IAM dataset, which is a collection of forms of handwritten English text, manually annotated with 6 named entities in the Tusselman et al. 2021 work. So the annotations were manually done in order to avoid the potential errors of automatic taggers. 657 writers have contributed to the creation of this dataset. It comprises 1,539 pages, 5,685 sentences, that is just above 100,000 words. So here we will discuss the most relevant previous work. So the method that is presented here tackled the joint OCR and NER from historic handwritten text of the Esposalles dataset as a sequence-to-sequence task. Their architecture combines a pre-trained ResNet 50 for the feature extraction from input images, and an encoder-decoder transformer to translate the visual features of the handwritten text into recognized numerical text, where each named entity is labeled with a category. Images are passed through the CNN to yield a stack of feature maps, basically a 3D matrix, which is then flattened to become a sequence of feature vectors, being the embedding sequence of the visual components that constitute the image. Combined with the positional encoding of the input sequence, self-attention mechanism is applied inside the encoder layers, resulting in an updated, more contextually informative representations of the input. The ground truth is in turn fed to the decoder mask multi-head attention to perform mask self-attention on elements of the ground truth text. The most essential part is the next one, cross-attention block of the decoder. So that is used to align encoded representations of the visual features to those of the characters and tags, for the model to understand the relationship between elements of both modalities and to understand what visual shapes and features constitute which characters. So the performance of this model correlates with the quality of the learned representations. And if we get to improve the representation learning capabilities at the encoder and decoder level, we will end up with a new state-of-the-art that outperforms the previous work. Also, we think that it is important to note that full attention is employed in this architecture and at the encoding stage, meaning that all elements will attend to each other, regardless to how distant they are. And we assume that this might lead to the involvement of noisy information in the latent representations of the input. This is based on the hypothesis that elements only relate to a local semantic context. Furthermore, we believe that there's still room for improvement of the decoding stage. Our goal would be to reinforce the alignment of elements from the input to those of the ground truth, which is currently happening by means of cross-attention only. So I guess this brings us to the proposed model. So here we see an overview of the proposed model, which we consider to be an enhanced version of the previous architecture. The goal is to change the encoding step in a way that each element in the input is only aware of a local context, so that its resulting latent representations are more pure and expressive and less noisy. To that aim, we replaced the conventional transformer encoder with a graph transformer. So the graph transformer was introduced in Dwivedi et al. 2020, and it allows to apply the self-attention mechanism on graph structures to update graph node representations. In our approach, we used the sequence of visual feature vectors to initialize the nodes of an initial graph, and each node's neighborhood will be determined based on its original position of the stack of feature maps outputted by the CNN. So we will have two types of visual features, those originating from the first and last lines of the stack of feature maps, and those from in between. Obviously, nodes coming from the center will have more edges and connections in the graph, because we assume that text in the center is more semantically relevant to more elements and should reach a longer up and down context or a wider up and down context than elements at the beginning or the end of the document. So in this pipeline, the first block of the architecture would do the following. The CNN would output a stack of feature maps. The feature vectors are retrieved from that stack of feature maps and are used to initialize the graph node representations. Then each node's representation would be determined based on its original position on the stack of feature maps. After that, the initial graph goes through the graph transformer layers, which combines each node representation with a positional encoding and updates it with a sophisticated weighted sum with respect to its direct neighbors. So the new representation of each node will only take into account the nodes that are directly connected with it. And we explain this sophisticated form of the weighted sum with more detail in the paper. So this allowed us to employ a dynamic attention mechanism that uses different attention scopes or ranges while updating a node representation, depending on its original position in the stack of feature maps. So for the aim of avoiding unnecessary attention computations and to minimize the amount of noisy information, we employed this dynamic attention mechanism. So the node representations of the updated or latent graph are stacked back in a sequential form in order to fit the input shape of the cross-attention block of the decoder. Then in the decoding step, we enhance the process of aligning text to visual features by means of a graph convolutional network. So what we do is that we let the regular cross-attention block compute its own aligned representations, and we let a GCN to separately compute its own. Then we combine the aligned representations learned by both modules with a direct sum. So we combine them with a direct sum as illustrated here. And finally, we feed the combination to the softmax layer to generate a probability distribution over the vocabulary. And I guess this brings us to the benchmarking step to find out if our changes are indeed improvements. So in terms of how we compare to the state of the art, this table presents the performance of the top performing approaches that were tested on the Esposalles dataset. So first, we can see that the previous work, the transformer model, the classic transformer model, upon publication was the one with the highest score. And it also shows that our model outperforms the standard transformer architecture. Moreover, it shows that our model is the only one that performs better on the harder complete task, suggesting that it was able to use the extra annotations and the longer context to its advantage. Furthermore, our model scores the smallest gap in performance between the complete and basic tracks, suggesting that it is the most robust, stable, and less sensitive to the context length, and the number of classes among which it has to predict the annotations. So for the evaluation on the IM dataset, which was a further step of validation of the robustness or the use of our contributions, we used the F1 score to keep it comparable to works that have been tested on the IAM. So we also trained and evaluated this standard transformer on this dataset, and it is shown that it significantly outperforms other methods. Nevertheless, the GNN-based model, our model, still outperforms the standard transformer to gain the upper hand on all works that have been tested on the NER task on the IAM dataset. So to conclude, through this work, we proposed an enhanced version of the sequence-to-sequence transformer that we believe is a generalizable to a wide range of sequence-to-sequence applications. In short terms, our contributions can be stated as follows. We leveraged an attention-based graph neural network to encode inputted visual features. We also leveraged graph structures to define a novel dynamic attention mechanism. And we used the power of the message passing mechanism in the graph convolutional network in representation learning. And to be more specific, we employed this module in the operation of aligning visual features to characters and tags. So what we can conclude from this is that local and dynamic attention did indeed lead to encoded representations of a higher quality, thanks to the removal of noise. And also, following the multi-head attention module at the decoder level with the cross GCN led to a better alignment of visual features to characters and tags. Thank you so much.